By taking this course, you will go from knowing nothing about Microsoft SQL Server to be able to comfortably create a database, create tables, write SQL queries and other fundamental tasks. Throughout the course, you will be building a database from scratch. You will learn how to install Microsoft SQL Server Express 2019 on Windows 10 and the management interface known as SQL Server Management Studio. You will learn the fundamentals of T-SQL, or also known as Transact SQL, which is Microsoft's implementation of SQL. We will cover data types, creating database objects such as tables, views, functions and stored procedures. You will learn how to write queries to be able to fetch data from tables. You will learn about database normalization and table indexing. You will learn how to create an Azure SQL database and connect to it, and then deploy the database that you have created onto it. All source code is provided for each video within the course resources section so that you can follow along. This course will always be updated with new or updated sections. So let's start our journey. We have now reached the point where we need to install Microsoft SQL Server Express 2019. To do this, go to Google and type in download SQL Server 2019 Express. You will then need to click on the first result that is shown. Once you have done that, the following page will be shown. Click on download. Once the download has completed, click on it to run the installation. Click on yes. Now, once you get to this screen, click on basic. Accept the license agreement and then click on install. This may take a while, so I shall see you in a bit. Okay, once the installation has been completed, you will be presented with the following screen. In the next video, I will explain how we are going to install SQL Server Management Studio. We are now going to install SQL Server Management Studio. To do this, click the button that says Install SSMS. This will open a new web page. Once the page is loaded, click on the link that says Download SQL Server Management Studio. To save time, I have already downloaded this file. I'm then going to run the installation. I will then click on Yes. As requested by the installer, I need to restart my Windows 10 PC. So I shall do this, and I will see you in a bit. So, after restarting my Windows 10 PC, I then double-clicked back on the installation, and I was presented with this screen. I will then click on Install. Now this process may take a little while, so I shall see you shortly. That's it, just click Close and SQL Server Management Studio is now installed. In the next lecture, we will learn how to connect to our SQL Server instance using SQL Server Management Studio. See you then. Okay, with SQL Server Management Studio now installed, we need to be able to connect to our server instance. To do that, I'm going to click on Start, locate Microsoft SQL Server Tools, and finally click on Microsoft SQL Server Management Studio. This may take a minute or two depending on your PC specs. Once the application has loaded, you will be presented with this login window. The defaults are fine, so click on Connect. Once connected to the server, you will be presented with this window. Now, on the left-hand side, click on Databases. As expected, we don't have any yet. So, in the next lesson, you will learn how to create your first database. See you then. In this lesson, we are going to create our first database. In order to do that, I'm going to click on the New Query button. Once loaded, in this area I can type in T-SQL commands. These commands allow me to create tables, database and other objects. But for our case, we wish to type in the following. The create database command enables us to create databases, as the name suggests. Once I've typed in this command, I need to give it the name of the database that I wish to create, as so. Now, before I execute this command, I'm going to type a couple more as shown. The reason for these additional commands is, one, I wish to change into the context of my newly created database once it's been created. That's what the use database name command, in this case use my database. To execute the commands, you can either press the F5 key on your keyboard or go up to execute. In a moment we will get a success message saying our database has been created. Also notice down here we are in the context of our newly created database. This means we are able to create tables. In the next lesson that is exactly what we are going to do. See you then. In the previous lesson we created our first database. I wanted to use this lesson to correct some terminology whereby I mentioned the word command. I should have said statement, for example, the create database statement, and to also explain what the go statement does. In the example shown, you can see I have the create database statement and the use statement, but not the go statement this time. Watch what happens when I try to execute this. It fails. So why is this? The reason for this is because when we write T-SQL statements, such as the create database and the use statements, we need to separate them into separate batches. This is what the go statement does. It separates our T-SQL statements. So I add the go statement back in as shown, and then I will execute the code. And it works this time. Now with that said, we can finally continue on to create our first table. See you soon. Before we can create our first table for our database, I want to show you how you can select a database and load the new query window. Because a couple of lessons ago I mentioned that you can use the use statement to change your database, which is fine for when you have a new query window opened already. But when you load SQL Server Management Studio from the beginning and connect to your SQL Server instance, you will see that the new query window hasn't loaded. To load the new query window for a database in question, all we need to do is from the left-hand side menu, select the plus icon next to the database folder to expand it. Locate our database that we created earlier, right-click on it and select New Query. This will open the New Query window. The other way is by clicking on New Query from the top menu and then select our database from the list. Now we can create our first table. I will type the create table statement as follows. This statement needs to know the name for our new table. I will call it car names. We then need to surround it with open and close brackets, as so. Within these brackets we define our columns. To keep it simple for now, I will create two columns called car make and car doors. I then need to define the type of data that these two columns will allow. The car make column will allow string-based data, so I will use the varchar 10. Varchar allows for a variable amount of string-based data. The number 10 means that this column will store no more than 10 characters. Should a car make be more than 10 characters, the insert will fail. For the car doors column, I will set this to be tinyInt data type, which allows numbers through 0 to 255. The next part is to define whether a column is null or not null. What this essentially means is when data is inserted, can the data for the columns be blank or not? For this example, I will set both columns to not null, meaning they must contain data. And finally, when you have more than one column, as we do in our example, you need to specify a comma at the end of each column, but not the last one. I will now execute the code in order to create our table. Success! This table was created. We can view this newly created table by going to the left side menu, clicking the plus icon next to Tables to expand the folder. In the next lesson, I am going to discuss more on the common data types used for columns. As promised, in the previous lesson, I am going to be discussing the common data types that you will come across and be using throughout your career as a database developer or database administrator. As a reminder, a data type is used to constrain the type of data a table column will hold. Data types are also used with variables, table variables, user-defined functions, and within stored procedures. I will be discussing these as we progress through the course. To begin with, I will discuss the data types used for textual data. We have already used the varchar data type. This data type allows for a variable length character string, where n is the string size in bytes. So in our previous lesson we used a varchar of 10 for the car make column. This means we defined a variable length column of no more than 10 bytes in size. So if I stored a car make of BMW, which is 3 characters long, it will only take 3 bytes to store. Should you wish to store a text value greater than 8000 bytes, you can use the varchar max. This would mean you can hold up to 2 gigabytes per column. The char data type is of fixed length, so let's say that we defined a column to be char 20. We know that we can't store any string value with more than 20 bytes into the column. But what this also means is that if you have a string value for the word hello, which is 5 characters long, and you store this value within a column of char 20, then this value would take 20 bytes to store, not 5 bytes, because you use char, which is a fixed size value data type. The other two textual data types are nvarchar and nchar. These data types are used to store Unicode character data. For example, you can store data in such columns to handle 3 different languages, such as Spanish names, French names, and English names. Also, the amount of bytes is halved. For example, instead of 8000 bytes or 2 gigabytes, it's 4000 and 1 gigabytes. This is because of the additional overhead of storing Unicode-based data. In the next lesson, we will discuss the data types used for integers. When you wish to store exact number integer-based data, you have a choice of 4 different data types. These are tinyInt, smallInt, int, and bigInt. The differences are the range of integers that each supports for each value pair column, and the storage size in bytes that each data type consumes. For example, if I was to try and store the number 4 billion into a column with the int data type, I would receive an arithmetic overflow error. This is because the maximum integer supported for this column type is 2,147,483,647. When you need to store numeric data with fixed precision and scale, you have a choice of decimal and numeric. Both are used interchangeably. The precision is the maximum total number of decimal digits to be stored. This number includes both the left and right sides of the decimal point. The precision must be a value from 1 to 38, the default being 18. The scale means the number of decimal digits stored to the right of the decimal point. It's worth noting that scale can only be used in conjunction with precision. Scale is subtracted from the precision to determine the maximum number of digits to the left of the decimal point. Storage size ranges from 5 to 17 bytes depending on the precision used. When you need to store numerical data for pricing, you have the choice of the money and small money data types, and they are accurate to a 10,000th of the monetary units that they represent. For when you need to store date and time-based data, you have the following data types: date, time, small date time 2, and date time offset. The date, as the name suggests, is used to store date-based data. Time defines a time of a day. The time is without time awareness and is based on a 24-hour clock. Date time defines a date that is combined with a time of day with fractional seconds that is based on a 24-hour clock. Small date time defines a date that is combined with a time of day. The time is based on a 24-hour day with seconds always 0, and without fractional seconds. Date time 2 defines a date that is combined with a time of day that is based on a 24-hour clock. You can think of date time 2 as an extension of the date time data type, but as a larger data range. Date time offset defines a date that is combined with a time of day and is based on a 24-hour clock. The main difference with this data type is that it supports time zone awareness. Wow, that was a lot to take in, and you are probably thinking, what the heck was all that about? Well, I wanted to lay the foundations for the next section, whereby knowing what you have learnt so far about data types is to continue creating tables by using these new data types that we have just learnt, and inserting data into our tables, and showing the errors that are produced when you insert the wrong value into a column using a certain data type. It's also important to know about the different data types as they play a big role for when you're designing your database tables, which we will learn about in a later section of this course. I have only covered the basics of the data types and the common ones that you're most likely to encounter. For more information, I urge you to search the internet using the keyword SQL Server data types. Using our knowledge that we now know in regard to the common data types that are used within SQL Server, let's put this knowledge into practice. You will notice that I have already typed out the T-SQL code ahead of time. The reason for this is I didn't want to bore you with the sound of my typing on my mechanical keyboard. Don't worry, all the code that you see is available to download from the course GitHub page, as well as the course resources section, so that you can take your time to read over it and use it as a resource for the future. Not only are we going to be getting practice in creating tables in this section, I will also introduce you to two new SQL statements, the insert and the select statement. We will cover each of these statements in detail in a later section, as there is a lot more to them than what we are using for this lesson. You will also notice the green text on my screen. This is what's called a comment. The dash dash is for a line comment, and the / star * is a block level comment. Anyway, let's get started. I've already changed to the correct database. It's the one we created earlier called my database. I will highlight the code that creates the table called my integers. The reason why I've highlighted the table code is so that I can execute the code selected without running all the code contained in the new query window. To execute, I will press the F5 key on my keyboard, or you can click the execute button located within the top menu bar. You should have noticed that this table's code is pretty much the same code that we used when we created our first table, car names, apart from the new data types and column names. As you can see, the table was created successfully. You may have also noticed with this table's code that I've used square brackets for the column names. The reason for this is for the purpose of this demonstration, whereby I have named the columns the same as the data types. Without the use of the square brackets, this would have generated an error, because we are not allowed to use reserved words for column names unless we surround the column names in square brackets. I really advise that you don't name your columns like this in the real world. This was purely a demonstration. You will notice that I've commented out the insert and select statements. I will come back to those soon. In the meantime, we will now do the same again to create the other tables. After the tables have been created, we can now begin to insert data into them. To do this, we will use the insert into SQL statement. This statement needs to know the name of the table that we wish to insert data into and the column names. The column names are optional, but I always explicitly put them in and advise that you do the same. The reason for this is because you can easily lose track which data entry belongs to which column. You can see an error was generated when I tried to insert a number that was larger than the permitted value allowed for the tiny int data type. In this example, I tried to enter 1000. Let's generate an error for textual based data. This error was caused because I tried to type more text that's allowed for that particular column. As mentioned, string or binary data would be truncated. When inserting dates and times, I have used the keyword convert. This allows me to explicitly convert the string type into a date and time type, as shown. Let's discuss the select statement briefly. Essentially, the select statement is your number one go-to tool to fetch data from tables, variables, table variables, and amongst other uses. In our examples, I am selecting all the data from our created tables. The star means to select all the columns. When we discuss more about the select statement, I will explain when to use the star and when not to use it. For now, it's fine. Let's see all the data in our tables. And there we go. All the data that we inserted into our created tables. In the next lesson, we will take a closer look at the select statement. We are now going to learn about the select statement. But first, we are going to create a new database, some tables, and insert some data into these tables. We will be using this database on and off throughout the rest of this course. Again, the source code is available to download for you to follow along. I will go ahead and open this file in order to run the code. We have already seen the select statement briefly in the previous lesson, but now we have a whole couple of lessons dedicated to it. So what is the select statement? Well, it allows us to retrieve rows of data and one or more columns from our tables. It also allows us to use literal strings. It can also be used in conjunction with the insert into statement, but more on this later. I will open a new query window and I'll make sure that I'm using the correct database. Let's start by showing the select with a literal string. I will type select followed by the words and I will execute this code. You will notice that I have surrounded the words Hello SQL Server in single quotation marks. You can see that it printed out Hello SQL Server in the results pane. It's that simple, but when would you use the select literal in a practical sense? Well, let's see an example which leads us on to selecting columns from a table. A quick tip: whenever I'm working on a database and I wish to see what columns a table has, rather than using the GUI in SQL Server Management Studio, I use a stored procedure called sp_help, followed by the table name in single quotes. The output from this procedure is a little overwhelming, but we are interested in the second results table that shows the columns of this table. Let me type this out so you can see what I'm talking about. Using the products table, I would like to select the product type column and the product price column and show a message saying, for example, the jumper costs £65 along with the other products and prices. Let's discuss what we have actually done. First, I type the select and from products table statement. Doing it this way allows me to use the inbuilt IntelliSense that SQL Server Management Studio provides. So when I start typing a column name, it shows up within the IntelliSense. Let me execute this line of code to show the output. I used the concat function to concatenate the string literals and columns from the products table together. This function returns a string value. The concat function is only available from SQL Server version 2012 and above. Before this function was available, we needed to cast a non-string based column such as product price, which is of small money, into a string based column such as varchar. Let me show you an example. First, I will run the statement that will fail. The error message shown is cannot convert char value to small money. The char value has an incorrect syntax. I will now run the statement with the cast, which will succeed. As you can see, it's the same output from when we use the concat function. We will continue with our discussion on the select statement in the next lesson, where we will discuss aliasing. Starting from where we left off in the last lesson, I'm going to discuss aliasing using the select statement. Aliasing is used from where we need to join between two tables or the same table. We will cover joins at a later stage. Aliasing is also used to give columns a temporary name, and this temporary name is shown within the results output. Using the concat statement from the last lesson, notice that in the results pane the header shows no column name. If this was used in a report, having no column name does not make any sense. So with the help of aliasing, we can give this column a name. To name a column, I use the keyword as shown. I'll execute this code, and now the column has a name called my column. Let's see an example of using aliasing to rename table columns contained within the select statement. In this select statement, I'm selecting the column's product type and temporarily renaming this column to type of clothing and product price to be price from the products table. When I execute this code, the results show the new aliased column names. In the next lesson, I will discuss the insert into statement. We have already used the insert statement in the previous lessons, but now it's time to learn a little more about the insert statement and its variants, such as select into and insert select. The insert into statement, as its name suggests, allows for the inserting of one or more rows into a table. The syntax for this statement is shown, where table name is the name of the table you're inserting rows into. Col1, col2 and col3 are the names of the columns, can be more or less, doesn't have to be free, that you are planning on inserting data into, and val1, val2, val3 are the values respectively, again doesn't have to be free. The select into statement creates a new table and inserts the resulting rows from the query into it, where col1, col2 and col3 are columns from the source table, and new table is the new table that will be created. Each column in the new table has the same name, data type, null or not null constraints, and values as the corresponding columns in the select list. The insert select is similar in nature to the select into, whereby it needs a select query with the columns from the source table. Also, the target table needs to be created ahead of time using the create table or should already exist, and the columns from the source table should be the same type as the target table. Enough theory, let's get down to seeing some examples in action. In SQL Server Management Studio, I have already connected to our database called the Clothing Store that we created in the previous lesson, and I've also written the code ahead of time. As always, the code is available to download. First, let's see again the insert into statement, which you should be familiar with by now. In this example, I am going to insert a new customer into the customers table. Let's check the result. In the next example, I will use the select into statement. The top keyword means I only want to select the top two rows. In other words, the first two rows from the customers table. Again, I will check the results. We can also see the new table was created along with the same column type as the source table. Now, let's take a look at the into select statement. First, we need to create the table. Again, there should be nothing new here as we have already covered creating tables. I will execute this code. Next, we have the insert into statement. Again, I have used the top command, but this time specifying 3 rows. Now I will execute this code. Now let's check the results. Now to clean up, as we will not be using these tables again. To delete these tables, I can use the drop table statement followed by the name of the table to delete. So you may be thinking, okay, I understand the insert into, and that's for inserting rows into a table, but when would I use the other two insert statements? Let me answer that question for you. I have used insert select when I've needed to create a report table combining data from two different tables within the same database. I was not able to use a view in this scenario. A view? What's a view? Don't worry, again, it's something we will cover later on. I have used select into when I've needed to massage the data from within a stored procedure using temp tables, again, which we will cover later on. In the next lesson there will be a challenge that you will need to try and complete. In this very first challenge of the course, and with the knowledge that you have gained throughout the course so far, I would like you to complete the following. Create a new table called Customer Salutations, with one column called Salutation. Set it as a varchar 80 data type, and set this to be null. Insert a new row into the products table. You will need to use all the columns except product ID, and the new row needs to be some sort of clothing of your choice. Finally, use the select statement to select one row from the products table, returning only the product price column. You can use the help of the internet or use the code resources. Don't worry, I will go over the solutions in a moment. So pause the video now and have a go. So how did you do? Well, let's take a look at the solutions. First, the create table statement. I will go ahead and execute the code to create this new table. The next part of the challenge was to insert a row into the products table. I will go ahead and execute the code to insert the row. Finally, the last part was to select a single row from the products table, but only return the product price column. We have finally made it to the end of the first section. Great job! In this section covered a fair amount of the fundamentals. We covered the following. The select statement, we use this to fetch rows from our tables. Insert into and its variants, we use this to insert data into our tables. Create table, a database is no good if we can't create new tables. The different data types, and how the data types are used to constrain the types of data a column will accept. We created a database using the create database statement. We saw how we could use the concat and top statements. And finally, we used the drop table statement to remove some demo tables that we created. We still have a lot more to cover, so follow me into the next section. Congratulations on making it through to the next section. Allow me to explain what we are going to cover in this section. So you have some tables in your database, and you can add data to those tables. But how do you update and delete this data? How do you make sure you only affect data that meets a certain criteria? That's what the update, delete, and where statements allow you to achieve, and that's what we will be covering in this section. We will also cover adding new columns to an existing table and updating those columns. You will learn about primary keys and foreign keys, as well as the identity statement. We will then discuss table design, and finally talk about indexing and how it can help with performance. And to reinforce the knowledge that you have learnt in this section, there will be an end of section challenge. Just remember, after each section that you complete, you are building upon your knowledge. We will discuss the alter table statement first. It allows for the update, adding and removing of columns. Its syntax is very simple. You start with alter table followed by the name of the table in question. Then you use either add, alter column or drop column respectively. The add allows for the addition of a new column. you need to specify the name of the column and its data type. When you add a new column, its data type is always null, unless you are using a default constraint. The alter column is pretty much the same as the add statement, but rather than adding a new column, you need to specify the name of the column you wish to modify. Finally, the drop column drops the column from the table, but there are a few limitations. You cannot drop a column that has a check constraint or any other constraint for that matter. You will see this in the demo later. Okay, I have loaded up SQL Server Management Studio and connected to our database, the clothing store. Again, I have pre-written the code ahead of time. We will start with altering the customer's first name column. I will change the size of the varchar data type from 60 to 90. Next, I will add a new column to the orders table and name it delivery date. This will be a date data type. Notice I have not used the null or not null. This is because when adding a new column, the default has to be null. I will then add another new column to the orders table and call it isExpedited. This data type is a bit. You can think of this in terms of true or false, or value 1 or 0. The project manager has mentioned that they no longer need this column, so let's remove it. Trust me, this happens a lot in the real world. Next, we shall add a new column to the order line items table called order quantity, which will have a constraint. This constraint will be a check constraint. The check constraint allows us to use a conditional expression to ensure that the data we are inserting into this column meets the criteria of the check constraint. If it doesn't, the data is not inserted. When creating constraints, they start with the word constraint, followed by the name that you have chosen, and then the type of constraint. In our example, the check constraint is checking to see if the order quantity is greater than 5. Let me show you what happens when I try to insert a value that fails the check constraint. And one that will succeed. As mentioned already, you can't delete a column that has a constraint associated with it. Watch what happens when I try to delete the order quantity column. In order to delete this column, I need to delete the constraint. I can do this by using the drop constraint statement followed by the name of the constraint. Then I can delete the column. I will now add the column back as we will need it later on. Lastly, I will add a new column to the customers table called isActive. Again, using the bit data type, but this time using a default constraint. A default constraint allows us to specify the default value for the column, so when inserting data we don't have to specify this column explicitly in our insert state. I will set the default to be 1, meaning that all customers and new customers are set to active by default. Finally, the with values tells the default constraint that once you have been created, fill any existing rows in the table with the isActive bit set to 1 in our case. Next up, we will be discussing the where clause. The where statement allows us to add a search condition to our result sets. What this essentially means is that we can apply a filter to our result to only return rows that meet our search condition. The update and delete statements allow us to update our data in our tables or remove data from our tables. We can also use a view to update and delete data. This is called an updatable view. Although we will be discussing views later, the updatable view is an advanced subject and will not be discussed in this course. The syntax for the update statement is the keyword update followed by a table name, followed by the column name where the data resides that we wish to update, followed by the new value for the data in this column to be. The where clause is used to target only a subset of the data to be updated. The where clause is optional, and in the demos we will see what happens when you don't specify it. The delete statement allows for the deletion of one or many rows from our tables. Its syntax is the delete keyword, followed by from, the table name, and an optional where clause, followed by the search condition to target a subset of rows or rows to be removed. Let's head over to SQL Server Management Studio to see some demos. First, I will use the where statement to retrieve the customer record with the ID of 4 from the customers table. Next, we will update customer ID 3, last name, from Woodcock to Edwards. Let's see what this looks like before I make the change. Now, let's make the change. And finally, let's confirm that the customer last name was updated. Now let's delete a product from the products table that we no longer stock. And let's confirm if this product was removed. As you can see, no results were returned. This confirms that this product was removed. Now I want to show you what happens when you try to update or delete from a table without the where statement. Let's begin with the update statement. I will use the begin transaction statement first. This will allow me to explicitly roll back the transaction. We will cover transactions later. With the transaction started, I will update the customers table, setting the last name to be Jackson. Let's see the results. As you can see, all customers' last names were updated to Jackson. Not what you really want to happen in real life. I will now roll back the changes using the rollback transaction statement. Now let's do the same again, but this time using the delete statement. Now you see why using the where statement in conjunction with the update and delete statement is beneficial to only update in a subset of the rows or row, and how the where statement can be used with a select statement to perform a search condition of the return results. We will be using the where statement a lot more when we get to querying section of the course. Most tables in a database typically have a column or combination of columns that contain values that uniquely identify each row in the table. For example, in our database, the clothing store, we have an orders table with an order ID column. This column needs to be unique because we don't want two orders having the same ID. When creating the orders table, I use the identity keyword on the order ID column in conjunction with the primary key, because the primary key will enforce unique values for this column, and when using the identity keyword, I can guarantee that each new row that I add will have a unique order ID of incrementing values starting from 1, then 2, and so on for each row that I add. A foreign key is a column or combination of columns within the table that is used to establish and enforce a link between the data in two tables to control the data that can be stored in the foreign key table. For example, With our table called order line items, this table has a column called order ID. This column is related to the order ID column in the orders table, because an order line item can't exist without an order being placed. Using a foreign key helps enforce this. If we didn't use a foreign key, a user could insert an order line item into the order line items table without any reference of an order being placed. There would be confusion all over the place in the sales department. Identity is used on a column, typically in conjunction with a primary key. It allows for the automatic insertion of incrementing numbers into the column and is typically applied to an ID column. The identity statement can be controlled at creation time as to what value to start incrementing from and how much by. The default is always n plus 1, where n is the starting value of 1. We can change this to be identity 1245, 10, where 1245 is the starting number and 10 is to increment by 10 each time. When you specify a primary key constraint for a table, the database engine enforces data uniqueness by automatically creating a unique index for the primary key columns. This index also permits fast access to data when the primary key is used in queries. Indexing is such a vast topic, even books have been written about the subject. This course only touches the surface of indexing. I highly recommend doing an internet search for SQL Server indexing to help fill in any gaps and to learn more about the subject. You can think of indexing like a book. When you wish to search for a page, you use the book's index. For SQL Server, this index would be the clustered index. The book's index will tell you what page you need to go to. Our database and tables are small, but the topics you are learning in this course can be applied to larger databases. So imagine not having an index in a book and you need to search for a chocolate cake recipe, and that this book had 400 plus pages. You would need to search every page until you came across the recipe, but you wouldn't stop there, as there could be more than one chocolate cake recipe, so you continue searching until the end of the book. Wouldn't it be easier just to have an index? Well, when SQL Server doesn't have a clustered index created on the table, it needs to search all the rows of that table, which there could be millions, if not more. And this will cause the query to run slow. This process is known as a table scan. A non-clustered index is an index structure separate from the data stored within a table that reorders one or more selected columns. Non-clustered indexes can often help you find data more quickly than searching the underlying table. Generally, non-clustered indexes are created to improve the performance of frequently used queries not covered by the clustered index, or to locate rows in a table. Without a clustered index, a table is called a heap. You can create multiple non-clustered indexes on a table or index view, which is beyond the scope of this course. Let's see some demos of this in action. In the first demo, I will start by creating a new column on the Customer Salutations table and name this salutation ID with an identity clause and setting this column to be primary key, because currently this table is known as a heap. A heap is a table without a clustered index. Next, I will add a foreign key constraint to the order line items table, specifying that order ID is the key column and that this references the order ID column in the orders table. With this created, let's try and insert a row with an order that doesn't exist. You will see that I was blocked from doing so. Also, you will not be able to remove both tables, that is the orders table and the order line items table. If I wanted to remove the tables, I would first need to remove the constraint and then remove the tables. I would do this by using the alter table statement followed by the drop constraint statement. I will not run this code, but I left it here for you as a reference. Next, let's create a non-clustered index on the orders table for the order total column. But first, let's see what happens when I query this table, searching for an order total 23. Before running this, I will enable the option to show the query plan execution. This will enable me to see what plan SQL Server used to return this result. A query plan is created by SQL Server to determine the best way to get a result. There is a lot more to it than just that, but that's a simple explanation. Again, covering query plans is beyond the concept of this course, and whole books have been written about the subject, so feel free to search more on this subject using the internet. You can see an index scan was done. This is because there is an index on the order ID column and not the order total column. An index scan is essentially a table scan, but since this table has a clustered index applied, it's called an index scan. Doing an index scan on a table this size is not an issue, but if this table had thousands, if not millions of rows, then the query executed would become slow. I will go ahead and create the index now. Now I will rerun the query and see what the query plan looks like now. This time it did an index seek on our newly created index. An index seek is similar in concept to the book analogy that I used earlier. Next up, I will discuss table designs. Some instructors prefer to discuss database design at the beginning of their courses. I wanted to wait until now to discuss the topic, for the reason being is now that you have had some experience in seeing tables and creating them, and understanding the different data types and why it's important to choose the correct data type for your column. Now is a good time for me to introduce database and table design. I will use the term database design as a term to include table design from now on. Why should you bother with database design? Well, it's not mandatory, and sure, you can create a database and some tables and call the columns whatever you like, but the problem with this is, as you will soon learn, is that most likely the tables would not have any form of relation to each other. After all, that's what SQL Server is. It's a Relational Database Management System, or RDMS for short. There are 7 terms used to describe database design, and it's still an active area of study, so the landscape will most likely change in the future. The 7 terms are known as 1NF to 6NF, where NF stands for normal form, and BCNF, or Boyce Codd normal form. For the purpose of this course, we will only be discussing 1NF to 3NF, as these are the most likely normal forms you will encounter in the real world. Let's start our journey with 1NF, or first normal form. A relation table is in 1NF if and only if the data in a column has a single value for that row. First normal form enforces these criteria: eliminate repeating groups in individual tables, create a separate table for each set of related data, identify each set of related data with a primary key. For example, the top table has a telephone number column. Notice that customer ID 1 has 2 phone numbers. To make this table to be 1NF, we need to eliminate repeating groups of data per row. To do this, I will create an extra column called telephone number 2 and move the second phone number into this column. Also, customer ID is the primary key for this table. A table is in the second normal form if it fulfills the following 2 requirements. It is in first normal form. All the non-key columns are dependent on the table's primary key. In this example, you can see the top table has a column called product type. This column doesn't really describe the products table, it's more of a categorical column. This would be more suitable, to be moved to its own table called product types. Once done, we can create a foreign key between this newly created table and the products table on the product ID column. What we have done here is to satisfy the following statement. All the non-key columns are dependent on the table's primary key. Now that all the non-key columns such as product name, product description and product price are dependent on the primary key, that is, product ID, what this essentially means is that given product ID of 1, we can use the non-key columns mentioned above to describe what product ID 1 is. For a table to be in free-NF, it must fulfill the following two requirements. Be in 2NF, has no transitive functional dependencies. Looking at the free-NF example and the top table with the column customer salutation, currently this breaks rule 2, and that is, at present this table has transitive functional dependencies. What do I mean by this? Well, let's say that customer ID 2, which is Mary Doe, should get married to Jack Smith, and she wishes to change her last name to that of Jack's last name, which is Smith. We would also need to update her salutation as well. This is what a transitive functional dependency is. To fulfill free-NF, we can create a salutations table with a foreign key constraint to the newly created column called salutation ID. With our database, we currently have a table that's breaking 2NF rules, and that's the products table. In the challenge section, it will be your job to create this new table to hold the product types, but we will not add any rows to this table or remove the column from the products table just yet. We will make this modification in the querying section of the course. You will see why when we come to that section. Next up will be the closing challenge for this section. Another section completed, and now another challenge to put your knowledge into practice. Again, with all these challenges, feel free to look at the code as a reference or use the internet to help you, and always write the code out, don't copy and paste. So in this challenge I would like you to do the following. Number 1. Create a new table called product types with 2 columns. One column needs to be called product type ID with an int data type and identity clause. Also, this column needs to be created as a primary key. The second column needs to be called product type, and this needs to be varchar60, not null. 2. Create a new column in the products table called product type ID, set as an int data type. 3. Create a foreign key constraint from the new column called product type ID in the products table to the product type ID in the product types table. 4. Create a non-clustered index on the column product type in the new product types table. So go ahead and pause the video now. So how did you get on? Not to worry, if you got stuck, I will now go over the solutions with you. First, I will create a new column in the product table called product type ID. Next, I will create the new product types table. I will then add the foreign key. And finally, I will now create the non-clustered index. In the next video, you will learn what we are going to cover in the querying section of the course. Welcome to the new section. This section will take you to the next level to be able to start writing queries that actually mean something for a business. You will learn how to search for ranges in the data and chain in more than one search condition together using the where clause. We will also learn the following: common table expressions, aggregation of data, subqueries, joining between 2 or more tables, the order by clause, the group by clause, and the top offset fetch, which can be used for pagination. We will also cover transactions, and add in data to our product types table that we created in the previous challenge section. We will start with the where statement, and using what we know about the where statement, we will build upon this knowledge. For this lesson, I have added some more data to the orders table. You can download this file from this lesson's resources section. The file is called ordersdataseeding.sql, and it contains an insert statement which adds a few rows to the orders table. Management would like us to perform 5 queries. The first is they would like to know what orders were shipped between the 1st of February 2019 and the 1st of July 2019. I will execute the first statement. Notice I have used the between and keyword. This allows me to search a range. It could be dates or numbers. Secondly, they would like to know what orders were shipped between the 1st of January 2020 and 1st of December 2020, and with a value greater than £250. Thirdly, they would like to know the order IDs that haven't been shipped. For this query, I use the isNull search condition. This allows me to search for orders that have not been delivered yet. The fourth query, management would like us to write a query that return order totals between £20 and £70 and that have not been delivered. And finally, management would like us to return all orders not equal to £200. The left and right arrow brackets in SQL Server mean not equal. Essentially, that's all there is to it. I can guarantee that most of the time you'll be writing queries like the examples above. Of course, the data will be different. But talking from experience, the queries above are typically what a company would like to know. What happened between these dates? Or what customers have an order total in this range? As we progress through this section of the course, we will be seeing more examples of the where clause. A CTE, or common table expression, specifies a temporary named result set. CTEs are created from simple queries, that is, within their body contains a select statement. The syntax is with CTE1 as open and closed brackets some query statement, where CTE1 is the name of your CTE. And some query statement is the query. So when would you need to use a CTE? I use them to break up complex queries, especially complex joins and subqueries. The example that I will show next will hopefully enforce the subject a little more. CTEs are a little beyond the basics of this course in terms of understanding them, but I wanted to introduce them to you briefly so that you can do further research on the subject, and so that when you come across one in the real world, it's not so much of a shock. Let's head over to SQL Server Management Studio for a demo. In this demo, I have created a common table expression with the name called sales_CTE. You can see that it starts with the keyword with, followed by the name, and then the as keyword, followed by open and closed brackets. Within the brackets, I will define the body of the CTE, which is a select statement. Selecting the customer ID, the delivery date, you will notice that I've surrounded this column with the year function. This allows me to grab the year value from the date data type. I then use the as keyword to alias this column as sales year. And I have used a where statement on delivery date column looking for orders that have a delivery date. The isNotNull search condition allows the results to only return orders with a delivery date. After the closing bracket, you will see the select statement. I am selecting the columns from the CTE, that is customer ID. Notice I have also used the count function on this column, and I've aliased this column as total sales. Next, I am selecting the year column. Notice that this column is the alias column name from the sales CTE. I am using the group by clause in this query. The group by clause groups customer ID and sales year together. Let me show you an example to further illustrate the group by clause. I will run the following query. In its output, you can see it returns the customer ID and the delivery year column. We can see that we have customer ID 1 shown 2 times, customer ID 3 shown 2 times, customer ID 2 shown 2 times, and customer ID 5 shown 2 times. Next, we can see that the year 2019 and 2020 are shown twice. Let's quickly switch over to a theory slide to show more information. Going back to our group by statement, where we have grouped by customer ID and sales year, we can break this down. First, let's group the customer ID. You can see in the image shown on the left side that we have our customer ID column shown on the left, and on the right we have a second table showing those customer IDs. What this is showing, and what essentially the group by is doing, it's looking for all the repeating values and then grouping them into one group. So the 2 1s become one group, the 2 3s become another group, and so on. It's the same for the sales year. The 2 2019s become one group and the 2 2020s become another group. Let's go back to SQL Server Management Studio. With the theory out of the way on the group by statement, going back to the count function, which needs to be used with a group by statement, this will count all the customer IDs within a group of customer IDs. For example, customer ID 1 appears twice within the customer ID 1 group. We saw this in the previous theory slide. Next, I have the order by statement. The order by statement is sorting on the total sales aliased column. By default, the order by statement sorts in ascending order. We can change this to sort in descending order by adding the keyword desk as shown. Let me run the code so you can see the output. As a rule, you need to use the group by statement whenever you are using any sort of aggregation function or using the count function. Let me show you what happens when you use the count function but don't specify the group by statement. We get an error in the select list because it's not contained in either an aggregate function or the group by clause. Next, we will be looking at how we join between more than one table. So far, the queries that we have seen and written have been used to fetch data from a single table. In the real world, you will certainly be required to write queries that fetch data from one or more tables. To help with this, we have 4 join statements. They are the inner join, right outer join, left outer join, and full outer join. Allow me to explain each one. The inner join returns records that have matching values in both tables. The left outer join returns all records from the left table and then matched records from the right table. The right outer join returns all records from the right table and the matched records from the left table. The full outer join returns all records where there is a match in either left or right table. This will become a little clearer when we see some demos. We have been asked by our boss to write a query that returns all customers and orders that have a delivery date set. I will execute the first query. This failed. The reason why this failed is because the column is ambiguous, meaning that since customer ID is in the customers table and the orders table, SQL Server doesn't know which column to join on. This is where the help of the as keyword comes into play. In the second query, I have used the as keyword after the table names and named the tables as C for customers and O for orders. I then have to prefix the customer ID columns with these alias names. Before I run the query, let's discuss it some more. The select, from and where statements you should be familiar with by now. The inner join statement takes a table name to join on, in our case the orders table. Next, the on keyword is used. This takes the 2 column names that we are going to join on, separated with an equal sign. Normally, the 2 joined columns are backed by a primary key and foreign key and usually have an index created on them. I will execute the query. Notice that we get back duplicates, that is, Katie is shown twice. The reason for this is because the inner join returns a match for each row, so even though we only have one Katie in our customers table, Katie has more than one order in the orders table. To remove the duplicates, I will use the group by statement on the customer ID and customer first name column to group the repeating data into groups. I will execute this updated query. As the results show, we don't have Katie appearing twice now. This satisfies what our boss wanted. He wanted to know all customers that have orders with a delivery date set. In the next lesson, we will cover the outer joins, and I will introduce you to a new keyword to remove duplicate data from our result sets. Now that you have seen the inner join, let's take a look at some simple outer joins. First, let's remind ourselves what the orders and order line item table looks like in terms of the data. I'm using select star on both these tables. I think now is a good time than any to explain why you should avoid using the select star on your production databases. See, I didn't forget. I did say that I would explain why, I just wanted to wait until the querying section of the course. The reason why you should not use the select star is for performance reasons. Ask yourself, do you really need to select all columns from a table? Okay, admittedly our tables don't have many columns, but what about a table with 10, 15 or more columns? By limiting the columns returned, we can make better use of indexes that consume less space in memory when our queries execute. This is by far the best reason to limit the columns in a select statement. Less memory means fewer storage reads, fewer CPU cycles and faster queries. Using select star is fine when you are testing a non-production database like we are. Anyway, let's get back to outer joins. So let me execute the two select queries to get the data returned to the results screen. Notice that we don't have an equal number of orders to order line items. In the orders results set, I have 8 rows. In the order line items results set, I have 6 rows returned. This was done by design for the purpose of this course. Before I execute the inner join query in conjunction with the left outer join, notice the go between the two queries. As a reminder, the go helps separate the batches. Both queries would run fine without it, but I like to be explicit when I'm executing more than one query at the same time. Next, I have added the distinct keyword after the select statements. What distinct does is to remove any duplicate rows from appearing. Essentially, it's looking at the columns in the select statement, which are order ID and order total. It then looks for any duplicate values within these columns and removes them from being returned in the results. Don't worry, it does not remove the duplicates from the columns in tables. Our data is still there, duplicates and all. Now I will execute the query. Let's compare the results. The top result set is from our inner join. The result set returned order IDs 1, 2 and 3. Next, our bottom result set is from our left outer join. Notice that it returned order IDs 1, 2 and 3, but this time we have orders 4 to 8. Also notice the null values in the far right order ID column. So what's actually happened? Let me explain. The left outer join takes the left input table, in our case that's the orders table, and matches all the rows to the right input table, which is the order line items table. We are performing a match on the order ID columns on both tables. So far this sounds like an inner join, but now the left outer join continues to show the results even when there are no matches. That's why we get orders 4 to 8 showing up. We can summarize the left outer join as follows. The left outer join keyword returns all records from the left table, orders, and the matched records from the right table, order line items. The result is null from the right side if there is no match, and that's exactly what we have seen. The right outer join is exactly the same. The right join keyword all returns rows from the right table. order line items, and the matched records from the left table, orders. The result is null from the left side, when there is no match. I will execute the query. The full outer join keyword returns all records when there is a match in left order line items or right orders table records. Essentially, we get all rows back. Again, I will execute the query. In the next lesson, we are going to take a look at a new keyword called the offset fetch. This is normally used to perform pagination. I have used the offset fetch keyword in applications that I have developed that I have needed to perform some sort of pagination. In this demo, we will create a new table called demo rows. We will delete this table after the demo. This table contains a column called row ID, and it's set as an int data type and use the identity keyword. Next is something new. The row number column is called a computed column and gets the value of the identity column when a row is inserted. I needed to cast the row ID into a varchar so that I could show some text saying row number 1 or row number 2 and so on. A computed column is a virtual column that is not physically stored in the table unless the column is marked persisted. A computed column expression can use data from other columns to calculate a value for the column to which it belongs, which is what I have done with the row ID being converted to a varchar. Computed columns are an advanced subject, so I will not go into detail in this course, but again I wanted to show you one as you will see them in the real world. I will now go ahead and execute the create table statement. Next I have an insert into statement, but this time I'm not specifying any columns. I've only specified the table. The reason why is there are no values for me to insert into the row number column as it's a computed column, as I've already explained above, and it gets its value from the row ID column for every new row inserted. And you already know that an identity column automatically generates incrementing numbers. So for me to use the insert into statement like I have, I needed to use the default values statement, which basically means use the default values for the column. Next, I use the go keyword followed by 500. This means I would like to run this insert statement 500 times. A little overkill for example, but it gives us a table with 500 rows of data, plenty for this demo. Now the fun part. The first query returns the first 10 row numbers. This is used with the offset 0 rows, then fetch the next 10 rows only. One caveat to this is that the offset fetch can only be used in conjunction with the order by clause, so I'm ordering by row ID. The next query is the same, but this time I'm offsetting by 10 rows and then fetching the next 10 rows. The last query offsets by 50 rows and fetches 10 rows. You can see how offset fetch could be used in an application. The application would send some parameters to a stored procedure. See, I've given a hint as to what is still to come in the course. That has an offset fetch statement specifying what page to offset by and how many rows to return back. Let's clean up by removing this demo rows table as we no longer need it. Our next lesson is to look at aggregation and subqueries. We are now going to learn about some of the common SQL Server aggregate functions. An aggregate function performs a calculation on a set of values and returns a single value. Aggregate functions ignore null values and are often used with the group by clause of the select statement. The ones that we'll be looking at are AVG for average, max gets the maximum value of a column, min gets the minimum value of a column, and sum, which adds all the values together in a column. Next, we will learn about subqueries. We will see some examples of simple subqueries and correlated subqueries. A correlated subquery is a subquery that has columns within the inner subquery that are dependent on the outer subquery. Subqueries can be hard to understand to begin with, and they can get rather complex. This was one of the reasons why I wanted to show you a common table expression, because a CTE can be used to make complex subqueries not so complex. Let's see some demos on aggregate functions and subqueries in action. First, a simple subquery using the in keyword. The in keyword is used to determine whether a specified value matches any value in a subquery or a list. So here I'm saying where product type is in the list of product types that we currently have stocked. Let me execute the code so that you can see the results. Next, a more complicated subquery using joins. What this query is doing is returning the maximum order total for each customer that they have placed. I shall execute the code so that you can see the results. Next, a correlated query. This query again is using the in keyword. This subquery has a reference to the first order's customer ID column called here as o.customerID. This subquery is returning all those customers that have an order total of less than £56. Finally, I have shown here a query with all the common aggregate functions. The min returns the minimum value, max returns the maximum value, average the averaged, finally, and sum returns sum of all values. I will run the query for you to see. In the next lesson, we are going to take a look at transactions. A transaction is a single unit of work. If a transaction is successful, all of the data modifications made during the transaction are committed and become a permanent part of the database. SQL Server follows the ACID principle. ACID is an acronym for Atomicity, is an all or none proposition. Consistency guarantees that a transaction never leaves your database in a half-finished state. Isolation keeps transactions separated from each other until they're finished. Durability guarantees that the database will keep track of pending changes in such a way that the server can recover from abnormal termination. Even a simple select statement runs in a transaction. There are three common types of transactions. Auto-commit transactions. Each individual statement is a transaction. This is what we have been using throughout the course. Explicit transactions. Each transaction is explicitly started with the begin transaction statement and explicitly ended with a commit or rollback statement. We saw the rollback when we were learning about the update statement. Implicit transactions. A new transaction is implicitly started when the prior transaction completes, but each transaction is explicitly completed with a commit or rollback statement. For this course, I will only be discussing auto-commit and explicit transactions. Let's see some demos. Here I am using a select statement to select all rows from the orders table. This is an auto-commit transaction, and we have seen these throughout the course so far. If you were to add begin transaction before the statement, it automatically makes the transaction explicit and holds a lock on the table or table row until the transaction is either committed or rolled back. In this example, I am explicitly typing begin transaction, followed by an update statement. I will run this and it says the command was successful. Now I will open another query window and do another select start and search for the order ID that we are updating, which is order ID 3 from the orders table. Notice that I'm blocked from doing so. This is because my update transaction has put a lock on that row, preventing other sessions from trying to read the data until I either commit or roll back the transaction. Let me commit the update transaction to release the lock. The reason why I was prevented from reading the table whilst the update transaction was active is because by default SQL Server uses an isolation locking level called read committed, which prevents a session from reading any data whilst an update is being performed for that row. This is a safety mechanism because, for example, you wouldn't want to return a value that was out of date that is in the process of being changed. But if I was to run a select star and search for an order ID that isn't being updated, this will work. That was a brief overview of transactions, but since this course for beginners to SQL Server, I feel that's enough to begin with on the subject. Our final lesson for this section is to use the knowledge that we have gained throughout this section and write a query that will enable us to populate the data for our new product types table. It's now time for us to populate our new product types table. As a reminder, currently we store the product types such as jeans and shirts among others in a column within the products table. From our lesson on database design, as it stands the product table violates the 2NF or second normal form. Let's work through the demo where we will make the products table to be 2NF. First, let's select the product type column from the products table to remind ourselves what the data looks like. If this was a big table with loads of rows, doing what we have done is certainly not the best way to do this. That is, selecting all the product types from the products table. What I would have done was to use a select distinct. The reason why I did it this way was I wanted to show you that we have duplicate rows returned, that is, jeans appears twice. With that in mind, the next statement I am using the insert into select. Remember that this statement, for this to work, needs to have a table already existed ahead of time. I have used the distinct keyword here to return only distinct values, meaning I don't want any duplicate data rows, such as the example above whereby jeans was inserted twice. So what I am doing here is inserting all the distinct clothing types such as jeans, shirts and jackets into the column of the product types table. I will execute the query and then check the results. Next is the complicated bit. I have started an explicit transaction. Then I have created a CTE, in this case it's called CTE1. This contains a select statement and a new keyword called cross-apply. The cross-apply statement behaves in a similar fashion to a correlated subquery and behaves in the same way as an inner join, in the sense that it retrieves rows from the top query and finds matching rows with the bottom query. So our top part of the query has columns product ID, product type, which comes from the products table, and product type ID, which is from the inner query named as PT. Inside the inner query we have a select statement, but the where statement is performing a match for us on the product type from the top query known as the outer query, and the product type from the inner query. Think of it this way, you have two buckets, you take a card out that says jeans, you then go to the other bucket and look for a matching card that says jeans. Even if there is more than one card that says jeans, you still take it out. When there are no more matches, you go back to the first bucket and take out a card that says jackets. You go back to the second bucket and look for matching cards that says jackets, and so on. Next we have the update statement. Again, I am using the cross-apply statement here as well. This time I am selecting one row from each of the matching product ID from our CTE, which is CTE1, from above, with the product ID from the outer query, which is a column from the products table. I am then setting the product type ID column of the products table to be the return product type ID from the cross-apply operation, or the inner query. This I have named as the letter A. I will execute the query and check the results. All looks good to me, but let's say this didn't go according to plan and we needed to revert the changes. I will use the rollback transaction for this and show you the result. Notice from the results that our changes have not been applied. That was to be expected as we use the rollback transaction statement to undo the pending changes to the table. I will rerun the query again and this time commit the changes. Next, I will remove the old product type column from the products table as we no longer need it. If this lesson seemed hard to understand, then don't worry. It takes time to understand some of the concepts shown, and some of the statements, such as the cross-apply, are more of an intermediate level than a beginner's course. The reason why I'm using these new statements is that I hope you are motivated to do more research into them and to make you aware of them. That's it for another section. In the next section we are going to be looking at stored procedures, functions and creating views. In this new section of the course we will be learning about the programmability features of SQL Server, which includes the following: stored procedures, table and scalar functions, views. With these features we have more control over our SQL code. So let's move on to discuss stored procedures. What is a stored procedure? A stored procedure is a prepared SQL code that you can save, so the code can be reused over and over again. So if you have an SQL query that you write over and over again, save it as a stored procedure and then just call it to execute it. Stored procedures accept input parameters and can return values in output parameters. Let's see a couple of examples. In this example, we will create a stored procedure that creates a new customer for us and then returns the new ID of this created customer to the results screen, along with the customer as well. First, let me explain the code. We have drop procedure if exists, followed by the name of the stored procedure, which in our case is called insert new customer. The reason why I'm using this statement and instead of an alter statement like we would with a table if we wanted to make changes to the procedure is because at some point the alter keyword for procedures will be depreciated, meaning Microsoft will move it in some future versions of SQL Server. Next, I have the go keyword to separate the two batches. Next, I have the create procedure statement followed by the name of the procedure. Again, this is called insert new customer. Next, I have the parameters section of the procedure, enclosed with open and closed brackets. This part of the procedure is optional, even when you have parameters such as input or output parameters. I like to put them in anyway, as it makes the code easier to read. Parameters are defined with the @ symbol like you would use in an email. They also have a data type. Notice that with the @new customer ID parameter, this is an int data type, but it also has the keyword called output tagged onto the end. The reason for this is to let the procedure know that it has at least one output parameter that it should expect to be set. Next we have a begin keyword which has an end keyword as well. This is not needed, but I like to be explicit to mark an enclosure of T-SQL statements. Then we have the insert into statement, and notice the values part of this statement, and that this is rather than typing in the values, then I would like to be inserted into the columns. I have now used the names of the input parameters. Next I am setting the @new customer ID output parameter to be the ID of the newly inserted customer. I have achieved this by using the function scope_identity, which returns the last identity value inserted into an identity column in the same scope, such as this stored procedure. Next, I have a select statement using a where clause and again filtering on the last inserted identity values using the scope_identity function. After the end keyword, I have declared a variable as an int data type. Notice that the parameter and variables are declared in the same way, and that is using the @ symbol, and again they both have data types. Parameters and variables are essentially the same thing, but the naming of the two are different depending if they are in a parameter or not. Next, I am calling the store procedure. This is done by first using the keyword execute, followed by the name of the procedure, and then for each parameter that we have, I'm assigning it a value. So at first name Ben is assigned to the parameter, followed by the at last name. The parameter at new customer ID has been assigned the variable at customer ID, and again I have needed to use the output keyword here. The reason why we need to specify the output here as well is so that the store procedure knows what this variable will hold, the returned value from this procedure. Finally, the select at customer ID will output this value to the results screen. I will now execute the code. The first result set is from the select statement contained within the store procedure. The second result set is from the select statement selecting the value from at customer ID. The body of the store procedure could be any statement you like. It could be an update statement or a delete statement. Let me show you another example. This procedure selects just one customer using the top keyword. Notice that this time I have not specified any parameters. Of course, this procedure wouldn't be very useful in the real world, but it was more to show you what the procedure looks like without parameters. I will execute this procedure. Next, we will take a look at table and scalar functions. In this course we will learn the following functions: scalar functions and table valued functions. Scalar functions are used to return a single value. They are used in select and where statements. A table function can be used in the from clause of a select statement and are used to return a result set. Let's see some examples of them. In the first example, this function is a scalar function and it returns the status of each order. Let's talk through this function's code. First, I have the create or alter function statement, followed by the name of the function. In this case, has order been delivered? Again, like in the stored procedure section, with the open and closed brackets, followed by a parameter which is at deliver date, and this is a date data type. A scalar or table valued function must return a value, whereas a stored procedure doesn't have to. I then specify that this function returns a varchar data type. Then we have the as keyword and the begin and end statements to enclose the body of the function. I am then declaring the variable at delivery status as a varchar. I am using the if statement to perform some conditional logic. The condition is checking if the parameter at delivery date is null. If it is, then the true statement is executed, setting the at delivery status to be not delivered. If the condition is false, then I am setting the at delivery status to be delivered. Finally, I am returning this back to the caller, which is what the return statement is for. After the function code, I am using a select statement. I am selecting the following columns: order ID, customer ID, delivery date. Notice that I have called the function from within the select statement. When calling a function, you need to use the full name, that is DBO and the function name. DBO is the default schema. You can think of a schema as a namespace. I've not included them in this course as of yet. I then pass the column delivery date into this function within the open and closed brackets. I have aliased this column after the function call to be order status. I will now execute the code so that you can see the results. In the next example, I'm creating a table valued function. The header is the same as the scalar function, but things get different after the parameters section of the function. Here we need to specify the statement returns table. This tells the caller that this function is a table valued function in that it returns a table. Then we have the as keyword followed by the return keyword. I'm using a simple select statement, and the where statement has a search condition that is looking for ordered totals that is greater than the value stored in the parameter called ordered total. Finally, I am calling this function. Notice that I have called the function from within the from statement, and that I didn't have to specify the schema name, that is DBO. I then passed the number 34 into the function. Of course, this number could be any number. I will execute the code. The results shown are the orders that have an order total greater than £34. In the next lesson, we will take a look at views. A view is essentially a virtual table. Views can be used to hide complex queries. They can be used for backward compatibility for your applications. For example, suppose that an older legacy application that you have uses a column from a table, but that column has since been renamed. You can use a view to allow the legacy application to still use that old column, but rather than using the table, it would use the view. The view would have this new column, but it would be aliased using the as keyword to the name of the column before its name was changed. They help with security in the sense that you can assign permissions to a view for users without them having access to the underlying tables that this view uses. Let's see an example of them. In this example, we are creating a view that selects all customers and their orders. First, I use the create or alter view statement, followed by the name of the view that I am creating. Next, I use the keyword as. This indicates where the body of the view starts. In the body of the view, I have a simple select and inner join statement, nothing new that you haven't seen. Finally, I call the view by using the select star from the view, in our case, the get customers and orders view. I will execute the code. And that's all there is to it in regard to creating a simple view. Next up is a challenge for you to complete. Before we finish this section, I have another end of section challenge for you. In this challenge, I would like you to 1. Create a stored procedure called insert new product that inserts a new product. You will need to, for the product type ID column, use an ID from the product's type table. For extra credit, create one that returns the product ID as an output parameter. Number 2, create a view that selects all product names and the product types. Name the view as get products and product types. As always, the answers are attached to this video's resources. So pause the video now. So how did you do? Let's take a look at the solutions. First, the procedure. The procedure is essentially the same as the procedure that we created in the stored procedures lesson, just different names for the parameters and the tables. Don't worry if you didn't get it correct. I will execute the stored procedure code and show you the result. Next is the view. Hopefully you didn't struggle too much with this. In the next section, you will learn how to deploy our database into Microsoft Azure. We have now reached the point in the course where we are going to deploy our database onto Microsoft Azure that we have created throughout this course, and that's the database called the Clothing Store. I will not go into details what Microsoft Azure is and how to use it. That's not the purpose of this course. Before you continue, however, you do need to create an account. If you already have an account, that's okay. Let's get started. I am already logged in to my Microsoft Azure account. I'm going to click create a resource. I will now select the database link within the sidebar. Followed by clicking on SQL Database. Before I continue, I need to create a new resource group. I will call this resource group Database Course. And I will click OK. Next, I need to enter a database name. I have called it my database name. It doesn't matter what name you use, we will be deleting it shortly. I now need to create a new server. The server is the SQL Server. In this example, I have used Database Course as my server named. The server admin login is dbadmin and my chosen password, and my location being UK South. I will now click OK. Next, I need to configure the database. I'm going to use the most basic database that Microsoft Azure has to offer. I will click Configure Database, then the link that says Looking for Basic, Standard, Premium, and then click the link that says Basic. I will make sure that the storage is right down to 100 meg. I will then click on Apply. Finally, I will click on Review and Create. Everything looks good to me, so I will now click on the Create button. This can take a while, so I will be back shortly. Okay, the deployment has been completed and was successful. I will now click Go to Resource. I now need to delete the database but not the server. To do this, I will go to the resource group. I will select the database and I will click Delete. I need to type yes to confirm. I will click the delete button and the deletion is underway. The deletion was successful. I'm now left with the SQL Server. I will click into it. I need to know the following information: the server name, which in my case is databasecourse.database.windows.net. Let's head over to SQL Server Management Studio and connect to this database. Okay, from within SQL Server Management Studio, I'm going to click on the Connect button. I've already connected to this database previously whilst testing, but you will need to type in your server name, followed by making sure that SQL Server Authentication is selected, and your database admin password. I will click on Connect. I will sign into my Azure account. And I will click on OK. Now it's time to deploy our database to Azure. To do this, I will right click on the clothing store, go to Tasks, select Deploy Database to Microsoft Azure SQL Database, click on Next, click on Connect, type in my admin password again, click Connect, click on Next, and click on Finish. This process can take a few minutes, so I'll be back shortly. After a few minutes, the deployment was successful. Congratulations, you have now deployed your own database into Azure. Congratulations on completing the course. You should be very proud of yourself. You started with no to little SQL Server knowledge, and now you know how to create a database, tables, store procedures, and even how to deploy a database into Azure. Everything that you have learnt can be used in Azure as well. Although we have only covered the basics in this course, there is still a lot more for you to look into. As always, if you need any help, please ask in the course Q&A section. Until next time, see you all soon.